Welcome everyone, this is Math 105, Lesson 9, Direct and Inverse Variation. So in the Winter Olympics, we've got some ski events. You've got the downhill, the Super G, the giant slalom, and the slalom. And each of these races have different run lengths, and they're also run on courses with different steepnesses. Now downhill, that's the longest race, and the slalom is the shortest. So I'd like you all to think about these races and make educated guesses, conjectures, about the first two questions. How does the course length affect the run time for the race? And then number two, how does the steepness affect the run time for the race? Now we're going to test these conjectures by performing an experiment. This is the ski race simulation experiment. And so what we're going to do is we've got these three ramps, and this one's 1 foot high, 2 feet high, and 3 feet high. So we've got different steepnesses for the ramps. We've also got different run times. We're going to see how long it takes the ball to roll down the ramp at 2 feet, 4, 6, 8, and 10 feet for all three ramps. And that way we'll get a bunch of data exploring the relationship between the run time and the steepness, and the run time and the length of the race. Now, if you can't perform this experiment at home, check out the answer key and you'll see some sample data there, and you can look at that. So, I think we've got kind of an intuitive idea for what's going on, but let's really nail it down. And so that's the purpose of the next four questions. We want to look at the relationship between these two variables. So as ramp length increases, the run time is also going to increase. Okay? As you have to ski a longer run, it's going to take longer. That's pretty obvious. And as ramp length decreases, the run time decreases. Now, assuming we're keeping the length constant, what happens as the ramp height increases? All right, we're going down a steeper slope. All right, and in here, now we've got an opposite relationship. All right, as the height increases, we're going to go faster, so the runtime decreases. And then as the ramp height decreases, the runtime increases, because we're not going as fast. And so these are examples then of direct and inverse variation. Direct variation is when two variables change in the same way. As one increases, the other increases. And that's what we're going to explore first. So direct variation. And we're going to see questions worded a little bit strangely. Y varies directly with X, or sometimes it's written as X. It's kind of a strange way of saying it. I prefer with because it's more common. And so if you vary directly with X, we're going to use this equation, and this is the equation of variation. Y equals Kx. And K is called the constant of variation. So what we're going to have is we're going to have an equation like this, and we're going to find the value of K and plug it in there, and that's going to give us an actual quantitative relationship between the two variables. So let's see how that works with an example. So example 1, Y varies directly with X. And when you see that phrase, you know we're talking about direct variation, so we're talking about the direct variation equation. So first thing we should write that down, Y equals Kx. Make sure you can locate the correct equation for the way the question is worded. All right, now we're given two values. We're given an X value and a Y value. And we're going to plug those into the equation so we can find this value of K. It's a really special value in this equation. It's going to be very important. And we're given that Y is 72 and X is 12. So I'm going to plug in 72 here for Y and leave K and 12 for X. Now we'll solve for K. Right? So I'm going to divide by 12 on both sides, and K is 6. So now we've just found the constant of variation. And that's going to allow us to get the equation of variation that's specific to this problem. So we just plug in 6 here, and here's our equation, y equals 6x. And there is the equation of variation for this problem. And now we can answer a question. If we're given one of the values in the variable, we can always find the other one now. So these questions will always end with a question like this. Find the value of y when x equals 3. We're given one of the values. We want to find the value of y. So we're going to plug in 3 for x. Then we get y equals 18. So these questions will always have 3 answers. One is the constant of variation. Use that to create the equation of variation. And then answer a specific question. Your turn number 1. If y varies directly with x, and y equals 108 when x equals 6, find the equation that relates x and y. Right? That's the equation of variation. And then we're going to find the value of x when y is 72. All right, just a reminder, pause the video, go ahead and work it out, and come on back. All right, so there's our equation of variation, y equals kx. Now I'm going to plug in 108 for y, and 6 for x, so k times 6. And now we're going to solve for k. So let's get k by itself by dividing out the 6. And that gives us a k of 18. All right, so there's our constant of variation. And there's the equation of variation, y equals 18x. Now they want to know what's the value of x when y is 72. All right, so on this one, we just had to plug it in and find our answer. But this one's a little bit different. And we're given the y value. So I'm plugging in 72 for y. So we get 72 equals 18x. Divide by 18 on both sides. And x is 4. Now to better understand direct variation, we're going to write in words the relationship between the two variables. And we're going to do that by plugging in some values just to see what we get. So here we've got y equals 6x is our equation of variation. And what I want to know is, how much does y change by when we increase x by 1? So I'm going to plug in x equals 1. So I'm going to find y when x equals 1. So we got 6 times 1, and that's 6. Now I want to find the value at x equals 2. Right, we're increasing it by 1. And we get 12. So as we see, as we're increasing x by 1, y increases by 6. That's no accident because that's our constant of variation. That's what the constant of variation means. You can think of it as being the slope of a line. You may have seen that in prior math classes. The steepness of the line. Well, this is a line with steepness 6. So that means every time we increase x by 1, y increases by 6. Okay, go ahead and do that for the one we just did here. All right, so we got 18 when we plug in 1 and 36 when we plug in 2. As you see, y is increasing by 18 every time x increases by 1. And that's our constant variation. Your turn number 2. The pressure exerted on a scuba diver varies directly with the depth. Right, so pressure varies directly with the depth. Now we're given, if at a depth of 16 feet, all right, depth 16 feet, the pressure is 6.94 pounds per square foot. That goes in for P. Now we'll solve for K. Divide both sides by 16, and we get K equals, and you can always just round. Kind of a rule of thumb is to round to the same number of digits as the information that you're given. So we've got this to the nearest hundredth, so we'll round K to the nearest hundredth and get 0.43. All right, now we've got our constant of variation. Now I'll write the new equation of variation, P equals 0.43 D. So as the depth increases by 1 foot, the pressure increases by 0.43 pounds per square foot. All right, now we can find what's the pressure at a depth of 100 feet. So we're going to plug in 100 for D. Multiplied by 100, we get 43 pounds per square foot. All right, so those are some examples of variables that change in the same way. So one increases, the other increases. But as we saw during the ski race experiment, sometimes the opposite thing happens. Sometimes variables move in the opposite direction, and that is called inverse variation. So for example 3, we've got inverse variation, so we're going to need the inverse variation formula. Now this time, instead of x being alongside k, we're going to put it in the denominator. And so that means as x gets bigger, y is going to get smaller. Let's take a look at an example of this. And here we got to look for these keywords now. If t varies inversely with r, when you see that, when it varies inversely, then we're going to use this equation. Or this type of an equation. Maybe changing out the y and x. So t varies inversely, so t equals, and k like that. And it's varying inversely with r. So r goes down here in the denominator. So just directly translate that as you see it. T varies inversely with r. Now we know that t is 12 when r is 3. So I'm going to plug in 12 for t and 3 for r. Now we can solve for k. So we're going to solve for k. We're going to get rid of the divided by 3 thing, so I always do the opposite operation. Opposite of division is multiplication, so we'll multiply both sides by 3. And that way the 3's over here cancel, leaving just k. So k is 3 times 12, or 36. And we found the constant of variation. Now we can create an equation of variation using this. Plug in 36 for k. So t equals 36 over r. And there's our equation of variation. And that's the equation we can use to answer questions. Now we want to know what's the value of r when t is 18. So I'm going to plug in 18 for t. So now we need to solve for r. And this is one of those situations where it's algebraically, we only need 2 steps to solve to get r by itself, and they're a little tricky, so we're going to use that swap trick. Right? Swap the 18 and the r. That's all we have to do. So r equals 36 divided by 18. So make sure you remember that trick. It's a very useful one. Divide that out, and we get r equals 2. Your turn, number 3. If y varies inversely with x, and y is 3 when x equals 8, find the equation that relates x and y. So y varies inversely with x. I'm going to plug in 3 for y and 8 for x. All right, just like we did over here, we're going to multiply both sides by the denominator. I'll get rid of that. 8's cancel. K equals 24. So there's our equation now. Y equals 24 over x. There's our equation of variation. Now we want to know what's the value of y when x equals 6. All right, that one's just straightforward then. Just do 24 divided by 6 and we get 4. Next up, example 4. The cost of producing a single phone charger varies inversely. All right, cost varies inversely with n, the number of chargers produced. If 10,000 chargers are produced, it costs $2 per charger. So 2 goes in for C. 10,000 goes in for N. All right, multiply both sides by 10,000. And we get a constant of variation of 20,000. We're going to create the equation of variation, so C equals 20,000 over N. And now that we know, find the cost to produce one charger if 25,000 chargers are produced. So we're going to find the cost if we have 25,000 plugged in for N, the number of chargers. Divide that out. Is 0.8, so it costs 80 cents each. Your turn, number 4. We got the speed of a pulley. So speed varies inversely with diameter. Diameter goes below. If a pulley with diameter 6 inches turns at 150 RPM, find the equation. All right, we've got a diameter of 6 inches, so that's going to go in for D. And the pulley turns at, the speed, S, is 150. All right, now we'll solve this by multiplying both sides by 6. That gets rid of those. So we've got a constant variation of 900. So our equation becomes S equals 900 over D. Now I want to know what's the diameter of the pulley that rotates at 90 RPM. So 90 is the speed. 90 is going to go in for S. All right, swap trick. This is going to come up a lot. Make sure you know this one. Divide those out, you get D equals 10, and the units are inches. Now in all the prior examples, the variables were all to the first power. That's not always the case. This also works with higher powers. So for example 5, this one's worded a little bit differently. If y varies directly with the square of x. So y varies directly with the square of x, x squared. Right, so there's going to be our base equation in this case. Y equals 18 and x equals 3. So 18 over here. Plug in 3 for x. All right, now we got one more step on this one. We're going to evaluate 3 squared, so that's 9. So 9k on the right. Then divide by 2. And k is 2. And that makes the equation of variation y equals 2x squared. Now we want to know what's the value of y when x is 5. So we're going to plug in 5 for x. So y equals 2 times 5 squared, or 2 times 25, and y is 50. So the only difference between these two is the wording. So varies directly with the square of x, and we'll need 2 exponent there. So other than that, process is exactly the same. So just read these carefully and slowly and get the right equation to start with. Your turn, number 5. If a varies directly with the square of b. So a varies directly with the square of b. A equals kb squared. Now we want a to be 48. And b is 4, so 4 squared here. And 4 squared is 16. So divide both sides by 16 and get k equals 3. Alright, now we've got the constant of variation for our equation. So plug that in. A equals 3. Oops. Needs to write next. A equals 3b squared. And now we're given b equals 2. So a equals 3 times 2 squared, which is 3 times 4, or 12. All right, next example. The distance the ball falls varies directly with the square of the time. So distance varies directly with the square of the time. D equals kt squared. The ball falls 144 feet in 3 seconds. So distance is 144. And time is 3. So 3 goes in for t. That gives us 144 equals 9k. Divide both sides by 9, and we get k equals 16. So there's our constant of variation. Now our equation is d equals 16 t squared. Now we want to find the distance the ball falls in 9 seconds. So distance equals 16 times 9 squared. So we have 16 times 81. Or 1,296 feet. Go try number 6. The braking distance of a car varies directly with the square of the speed. If a car traveling at 40 miles per hour takes 80 feet to stop, find the equation. All right, braking distance varies directly with the square of the speed, s squared. Car traveling at 40 miles per hour takes 80 feet to stop. Distance is 80 feet. And 40 miles per hour, 40 goes in foot speed. Forty squared, 1,600, divided by 1,600 on each side. We get a k of 0.05. So let's plug that in. So d equals 0.05 s squared. Now we want to find the stopping distance of the car traveling at 70 miles per hour. So we're going to plug in 70 for the speed. And that gives us 245 feet. Now let's say we wanted to look at this previous situation in examples in your turn number 6, but we want to swap the variables. That means instead of varying by squares, we're going to have to do the opposite, square root. All right, so you have to read these very carefully. Example 7. The time t, the ball falls, right? T varies directly, so varies directly with the square root of the distance. So now it's the square root of the distance. So make sure you can differentiate between square and square root. If a ball falls 144 feet in 3 seconds, find the equation. So we got 3 seconds, k square root 144 feet is the distance. Square root of 144 is 12, so we got 12k over here, divided by 12, and k equals 1/4 or 0.25. That makes our equation Plug in 0.25 for k. We get t equals 0.25 times the square root of d. Now we're going to find the time it takes for the ball to fall 1296 feet. So time equals 0.25 times the square root of 1296. And the time is 9 seconds. Alright, so that's exactly the value that we started with in the other one. So what we did here was just reverse the process. We went from what was the ending variable last time to the starting variable. Your turn, number 7. The speed of a car varies directly with the square root of the braking distance. Alright, speed varies directly, square root of the braking distance. If a car is traveling at 40 miles per hour, so speed is 40, takes 80 feet to stop, so square root of 80. Find the equation that relates to S and D. Alright, square root of 80, rounded, that's 8.94. So 8.94k. Now divide both sides by 8.94. And that gives us a k of rounded 4.47. So our equation then is S equals 4.47 times the square root of d. Now find the speed of a car that takes 245 feet to stop. So speed equals 4.47 times the square root of 245. And S equals 70, exactly where we started with in the prior problem. And that's 70 miles per hour, that include the units. Example 8. All right, now we're going to look at some inverse variation. So y varies inversely with the square of x squared. Now we got y equals 4, and x equals 5, so we'll have 5 squared in the denominator. So that's 4 equals k over 25. Let's get rid of that 25 by multiplying in both sides. 25's cancel, and k is 100. So that gives us an equation of variation of y equals 100 over x squared. All right, so there's our k, there's our equation. Now we can answer, find the value of y when x equals 2. Plug in 2 for x, gives us 2 squared on the bottom. 100 divided by 4 is 25. Your turn, number 8. If c varies inversely with the square of d, right? C varies inversely with the square of d. And c equals 32 when d is 2. 2 squared on the bottom. That makes 32 equals k over 4. Multiply both sides by 4. So we got 128 for k. And that makes our equation c equals 128 over d squared. Now I've got our equation of variation. And I'm going to find the value of c when d is 4. So that's 128 over 4 squared, or 128 over 16. And so c is 8. Example 9. The intensity of light varies inversely. All right, intensity varies inversely with the square of the distance. Square of the distance. If the intensity 5 feet from the source, all right, we're 5 feet from the source, that is 5 squared, is 3 foot candles. The intensity, 3 foot candles. All right, now we're going to solve for K. So this is 3 equals K over 25, multiplied by 25 on both sides, and K is 75. So that makes our equation I equals 75 over D squared. Now we want to find the intensity at 15 feet, so our distance is 15. So I equals 75 over 15 squared. So 75 over 225. That is 1/3, or 0.3 repeating. And the units are foot candles. Your turn, number 9. The force of gravity, F, varies inversely with the square of the distance from the object, D squared. If the force is 36 newtons, so force 36, at a distance of 2 meters, we're going to find K. So that turns into a 4, 36 equals K over 4, multiply both sides by 4, and K is 144. So we'll plug that in, and we get F equals 144 over D squared. And there is our equation of variation. Now we'll be able to find the force at a distance of 4 meters. Distance is 4. I'm going to plug in 4 here. And it's 4 squared in the denominator. So that's F equals 144 over 16. So that gives us open. F is 9, and that is in newtons. So the force is 9 newtons. Alright, so that's it for today. Now this is going to be very important for next lesson when we do joint and combined variation.